Yeah, so I'm often in security and privacy venues, but I'm really excited to talk today about TANGO, Secure Collaborative Route Control Across the Public Internet, which is a collaborative work with these amazing researchers. So I want to start by asking a question. Is today's internet good enough for performance-critical applications? And to make this specific, imagine that we are a university and we want to collaborate with a small cloud provider. This cloud provider has better price and capabilities than other offerings. And we would like to offload some of our performance-critical apps that need to be reached from campus to this cloud provider. Furthermore, we want to talk to this cloud over the public internet. So we have like an IP transit link, and we don't actually have like a private peering with this cloud provider. But in this scenario, we run into a problem. And that's that the public internet doesn't offer any performance guarantees. Quite often, the latency can be too high or inconsistent. We could have an unacceptably high level of packet loss, and all of this hurts the reliability of our performance-critical applications. So there is one solution to this problem that you've probably heard a lot about, and that's to pay more money for different services which help solve this problem. One of these is edge compute, which means putting performance-critical applications at or in edge networks. The other one is network as a service, which is an on-demand offering where you can essentially reserve a point-to-point link for your applications. But there is some downsides to this. So small networks and underserved regions really can't compete. This is a map of Google and AWS's edge nodes. And as you can see, you really kind of have to be a hyperscaler to compete with this and have edge nodes all over the world. If we look to these sort of network as a service offerings, they can actually get quite pricey quite quickly. This is just for a 10G link to Chicago to New York, and it's $1,700 a month. So this is not always a viable option. And this brings me to the question of what would it actually take for the public internet to better serve performance-critical apps? Well, the first thing is we need to know what paths are actually available on the public internet. This is the path diversity problem. Secondly, we need to accurately measure along these different paths. And third, once we have these measurements and we have these paths, we need to make an informed routing decision that can actually put traffic on the best performing path. So what we're proposing is TANGO. This is a picture of me and my spouse dancing tango, and as you can see, it's a very tight dance with a lot of collaboration. We are proposing TANGO across the internet. We think that we can solve these problems by having edge networks at two sides of the internet collaborate with each other. So let me start by looking at the path diversity problem. This is historically challenging on the traditional internet because the routing protocol or border gateway protocol does not expose all available paths. It's sort of a one path per neighbor protocol. And in this diagram, edge 1 only has one possible path for going to edge 2, since it only has one upstream with AS5 or autonomous system 5. Edge 2 is seemingly in a better position because it has two upstreams, so it can choose which one it wants to send traffic out of. But it only has two paths available, and there's sort of four logical paths through this topology. So it's really only impacting the first hop of its traffic, not the entire path. So our solution to this is an algorithm that we call BGP Pathfinder. It's worth noting that this algorithm starts with absolutely no knowledge of the internet topology. And under these circumstances, it really only has one choice. It can make a default BGP announcement. And I'll just take a moment to explain how that works. The BGP announcement contains an IP prefix that it's advertising reachability for. It then propagates through the internet, and that installs routes into those routers' route tables that allow traffic to flow in the reverse direction. So in this diagram, the green is the direction of the BGP announcement, and the pink is the flow of traffic that corresponds to that announcement. So after making a default path announcement, we have one path, as good as we had before. But what we can do is we can actually suppress that path. So right now, I'm adding an attribute known as a BGP community to this announcement. And this particular community is telling AS1 not to export this route to AS2. So these are traffic engineering features that many ISPs support. And when AS1 gets this community, it will no longer advertise the announcement across this link. Well, this will simply cause the BGP announcement to find a new path to reach edge 2. But in doing so, we've actually exposed another path for getting from edge 2 to edge 1. So BGP Pathfinder can record that we found this new path with this particular list of communities. And then we can actually go and suppress that new path that we found. So now we added another community, stopping AS1 from propagating to AS4. This causes us to find the red path. If we suppress this path, we ultimately find the pink path, which is the last path in the topology, and we know the communities that generated all of these different paths. Now, if we try suppressing the pink path, what we find is that there are actually no more paths for edge 1 to reach, or edge 2 to reach edge 1. And this is actually a good thing, because it means that we've found all of the available paths in the topology, and at this point, the Pathfinder algorithm exits. I should mention that here we always sort of strategically suppressed right at the proper link where we would find the most diversity. Of course, the algorithm is completely black box. It doesn't actually know where that's going to be, so it tries suppression at all hops along the path. So once it's run this algorithm, BGP Pathfinder, the destination node, so edge 1, can announce different IP prefixes, each with these different community lists found by Pathfinder. So in doing so, each of these prefixes is going to propagate along a different path on the internet. And then when edge 2 goes to send traffic, it can choose which path it wants to use to reach edge 1 simply by selecting which prefix it wants to use to send traffic to. And I should mention that even though we were varying BGP announcements previously, at this point, once we start sending traffic, all the BGP announcements are stable. So we can change where the traffic goes just by changing the destination IP. So now I want to talk a bit about measurements. Now that we have the paths, we need to know how are they actually performing so we can pick the best one. Measurements also are challenging on the public internet in sort of this one edge setting. Imagine this edge wants to optimize its outbound routing, so it really cares about the performance of this green path because maybe it has a different way to reach this other node. But what does it actually see? Well, it sees round trip time, which right in the name includes the return path. So we get a noise signal introduced by the fact that we also see the return path. Furthermore, round trip time has edge network delays. So this client is over a wireless link. That link could be high loss, high latency, and all that inflates the round trip time as well. And finally, this client's application layer behavior also could impact the round trip time. So delayed ACK, or if the client is running slow and has a long TCP buffer, all of these will cause round trip time issues. Additionally, imagine that there is an adversary on the path. An adversary could try to manipulate round trip time, and we need to be robust against that. And finally, all of this has to be run at line rate. So our solution, once again, comes from cooperation. Each of the switches at two edges of the internet add a custom TANGO header using either programmable hardware or eBPF. The TANGO header allows us to measure only the one-way wide area component. So it's added by the first switch, and then it can get processed by the second switch. And as a result, we are simply piggybacking this measurement header on packets. We're not actually dependent on any type of behavior, by the application. Now, the adversarial point I made earlier is actually really important, particularly when you are going to make an informed routing decision based on performance. So there's actually an interesting traffic hijacking attack that is enabled by this, where if I'm an adversary and you were originally not going to send packets down my path, but I would like to hijack your traffic, so I'd like to receive your packets. And somewhat like a BGP hijack, one thing I could do is try to make my path look more performant. And if you're making a decision based on performance, all of a sudden you're going to send all your packets to me. So we need to make sure that the measurements we get out of these paths actually reflect what's happening in the network. And to do that, we protect several fields in the packet with cryptography. So first, we protect sequence numbers to make sure the adversary is not actually hiding loss and dropping packets. We protect timestamps to make sure the adversary doesn't pretend the route is faster than it actually is. And we protect route control messages. So if we need to send a control message from one edge to another, that's also protected with cryptography. Now you might be thinking, I mentioned this has to be at line rate, and there are going to be billions of sequence numbers moving through that switch every second. How do we encrypt all of those? Well, because traditional cryptography algorithms do not run very well on programmable switch hardware, we use something called a book cipher. Every sequence number corresponds to a specific index in a cipher book that is shared between the sender and the receiver. And you can generate the books just with a pseudo-random number generator. So when the sender sends a packet with a sequence number, it looks up that index in the book and attaches a 1-bit signature to that packet. The receiver simply looks up the corresponding index and sees if the bit matches, and if so, that's a valid signature. Now, this is a very short signature, and clearly an adversary has only a 50-50 chance that it's going to get it right. So this normally wouldn't pass for standard crypto. But we exploit the fact that for an adversary to meaningfully impact loss, they would have to guess thousands of signatures. Even at a loss rate of something like 2%, with all the packets flowing, there's going to be a huge number of guesses needed. And the likelihood of them actually successfully avoiding detection on all of these guesses goes down exponentially. So I want to talk briefly about route control. We now have different paths. We know how to measure them. But now we have to actually route traffic over the most performant path. So there's an interesting problem that particularly arises when you use one-way delay data. Here, edge 2 is sending to edge 1. And edge 1 gets to collect all this great data that would make a great routing decision. But it doesn't actually send the traffic. It's edge 2 that needs to know how to send the traffic. And it's non-trivial to actually get this data back from edge 1 to edge 2. It's coming in at line rate. It's coming quite fast. So what we do to solve this problem is that edge 1 simply collects all the statistics locally and computes whatever metrics it wants across those to make the best routing decision. And because edge 1 and edge 2 are collaborating, edge 1 actually gets to know what are edge 2's routing objectives. And when it realizes that edge 2 should change paths, it sends back a routing control message. So this is uniquely enabled by collaboration. We don't have to send the raw statistics back all the time. We simply send the control messages. So now I want to talk about an evaluation. So right off the bat, how many alternate paths did we actually find? So we ran BGP Pathfinder on 503 globally distributed nodes from the cloud provider Vultr. So this took about 30 minutes per pair, and you can parallelize it with multiple prefixes to make that time less. By default, Vultr was only giving us a single path to reach all the destinations on the internet. For 80% of the node pairs, we found additional paths. And on average, the median node had 3 paths for reaching another node. Additionally, some of the best performing nodes had up to 10 to 12 different paths. Now, can we actually beat the performance of the default BGP path with these alternate paths? To measure this, we took measurements from 25 globally distributed nodes to 2 destinations, Stockholm and Los Angeles. For each destination, we measured along multiple paths, and we took latency and loss measurements every 10 milliseconds. So what we found is that for many destination and source nodes, the optimal path found by TANGO had a 22% lower latency than the BGP default path. And this was almost as high as 39% for some nodes. Looking at this graph, we can see the frequency on the y-axis and the latency improvement on the x-axis. So where a peak lands on the x-axis, that's the sort of mean latency improvement for that node pair. Each node pair is a different trace labeled with the side. And finally, I had mentioned this crypto algorithm that I said we can run at scale. But that's quite non-trivial, as I talked about before. But we were actually able to implement this on a Tofino 1 programmable switch. The way it worked is that actually the signatures were sent to the switch in the data plane. So an off-switch device generated the cryptographic book and then sent the book to the switch in the data plane. The switch then recirculated the signature packets while it was writing a high-speed data plane register. What we found is that to write 2 to the 20 signatures, we were able to do that in 2.6 milliseconds, even when the switch was handling other traffic loads at the same time. And this is well good enough to keep up with 100 Gbps of TANGO traffic. And I think it's important to remember that the signature is 1 bit long, and the packet can be all the way up to an MTU size. So in conclusion, I think there are 3 really important takeaways from this. The first is that we actually can get alternate paths out of the public internet. It is not a 1 path per neighbor routing system. The second point is that these paths often do actually have improved performance over the default path. And finally, we can actually get trustworthy network telemetry to run at line rate in programmable switches. So I'd like to thank everyone for your time and end by taking any questions.